Okay, so proofs, the idea in chapter 7 is we're trying to do triangle congruence proofs. So we're going to be doing the side, 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 angle, and angle, angle, side, and sometimes afterwards we have to do things like CP, CFC. But you know how you start every proof is with the givens, and we're going to end the proofs, or at some point we're going to get to the side, side, side part. But what you're normally going to be missing is various sides and angles. So we are going to talk a little bit today about things to look for with these proofs. So here's some of the different things to look for so you can add angles and sides. So I'm going to number them. I think I have about 11. I'm probably missing some. I'm probably being a little redundant. But I would carefully write all of these down. The first thing is if you have an isosceles triangle. If you are given an isosceles triangle, you're going to know a few things right away. You're going to get a vertex angle or base angles, two of them. But if I have triangle A, B, C, and A is the vertex angle, I know automatically I can say that AB is congruent to AC by the definition of isosceles triangle. So that's the first one we're going to do. 2 is very closely related. So if I have number 1, or if I have two sides congruent, and remember the orientation does not matter. This triangle could be upside down, sideways. BC is not the base because it's horizontal. BC is the base because B and C are the base angles. And what that means is if I know AB and BC are the same, what I can say is that angle B is congruent to angle C. And again, you have to have a justification. There needs to be a mathematical reason. You can say that angle B and angle C are the same. And in this case, you are going to use the isosceles triangle theorem. The isosceles triangle theorem states that if you have a triangle with two equal sides, two congruent sides, you obviously have an isosceles triangle, and the angles opposite the equal sides, which means a cross, have to be congruent. They have to have the same measure. 3 is pretty boring because it follows. What if instead of giving you congruent sides, what if I gave you congruent angles? So if I have triangle X, Y, Z, what can I state? Well, I can state that XY is congruent to XZ. So I can mark this side equal to that side because they are opposite the base angles. So the reason I'm going to write down is not the isosceles triangle theorem because we're going backwards, and when we go backwards in math, that's called the converse. I've changed my if and then part. So converse to the isosceles triangle theorem. So if you have isosceles triangles, you're going to be probably using the definition of isosceles triangle, or the isosceles triangle theorem, or the converse to the isosceles triangle theorem. Number 4. Sometimes they tell you things midpoint or bisect. We are going to start with the midpoint or bisecting a segment. So if I have a triangle, this one is not isosceles. Triangle CAM, and I say, well, that shouldn't be M, but anyway. So there's two different ways I could phrase this. I could say, I could be given that P is the midpoint of MA, and I probably should have made PM and MP, but anyway. Or I might state something like CP bisects MA at P. In both cases, you are allowed to say that MP is congruent to PA. So definition of midpoint. Some people will get really fussy and say that with if it was the bisect one, you'd first have to say that P was the midpoint by definition of bisector, and then say that, and then do it. But I'm going to be fine if you say definition of bisect. I don't want to get too finicky. So the idea is if you know that this is the bisector or the midpoint, you know those two sides are equal. Well, you can also talk about, you don't talk about it as a midpoint, but we do talk about angle bisectors. So if I have a triangle, let's do a obtuse triangle just for funsies. And we will do triangle Tom just for fun. And let's make this an L. So if I tell you that OL bisects, so this would be a given, right? Angle TOM, what do we know? We know this angle and this angle have to be congruent. So I know from what we were given, the angle TOL is congruent to angle MOL. And what is my reason? Definition of angle bisector. I cut it in half. So hopefully everybody's good on that one. 6. This one's from quite a while ago, but it should. We did it an awful lot, so hopefully it's stuck. Anytime you see sort of a bow tie, you have something like this, and it could be vertical, which is sort of a big old hint, but the name actually has nothing to do with that. It could be horizontal, obviously it could be at some sort of oblique angle. What I want you to be looking at, so the orientation, remember, does not matter. I want you to remember that this angle has to be equal to the angle across from it. So let's say that we have our two back-to-back triangles. On this one, we know that triangle, well, remember, H has to be the middle letter. So if I'm doing the upper one, I can put the R or the I first. But the H needs to be in the middle, and the H needs to be in the middle on the bottom one, too. So SHC, for example, would be an example. And feeling very creative, let's go with A, B, C, D, E. My two angle C's are congruent, but you just can't say that angle C is congruent to angle C, because you've actually got 4 different angle C's. So we need to specify when it can be ambiguous, when there is more than one possible meaning. So I'm going to say that angle ACB is congruent to angle DCE. In both cases, some teachers will make you establish that they're vertical angles first, and I'm just going to say you can say either of those by the vertical angle theorem. So things to look for in your proofs. Number 7 doesn't come out a whole lot, but it is a good one to remember. There'll probably be a couple problems here and there. And what we are going to do is we are going to have a triangle. I know this comes as a huge shock at this point. So if I have a circle, well, it doesn't even matter that they're back to back. But let's say I call this A, this B, C, and D. The part I want you to concentrate on is that AB and AD have to be the same. Well, why? What do we call? A is the center of the circle, D is at the edge. What do we call that? We have a radius, A and B. Again, we have a radius. All radii of circles must be the same. So in this case, we could say that AB is congruent to AD. Our reason? Well, that's how, in this book, that's how we define circles. So definition of circle. We defined a circle to be a set distance from a center point on a plane. So that one's going to, could occasionally rear its head, so look for it. Number 8, another way to get a side or an angle, well in this case we're going to look for angles, is this is not an uncommon shape this chapter. Okay. This one throws people, you don't see it like this, but if I extend the lines, it seems to help. So I'm just going to extend the line. We did this a lot back in Geometry A. That we have here is if I'm given that, so I need to be given more information. I need to be given that OR is parallel to CA. If I'm given that, well, I've got parallel lines now with the transversal. So I can't say anything about this angle and this angle, but I can say that this angle and that angle are congruent. So I can say that angle R to C to A, this one right here, call it angle 1, is congruent to angle CRO, right up there, angle 2. Why can I say that? Because if I have parallel lines, then alternate interior angles must be congruent. This one isn't going to show up a lot right now, but once we hit 7.5, it'll be all over the place. And it's this upside down capital T symbol that hopefully is fused into your brain. And that symbol, hopefully you remember, means perpendicular. And hopefully you also remember that means that there is a 90-degree angle. We will be adding to this on the hypotenuse leg theorem. Right now, all you're going to be able to do is get a couple angles out. This is eventually going to help us with that ASS situation. But for right now, clearly not congruent triangles, but I can say something about two of the angles. So A, P, B, C, if I say that CP is perpendicular, so this will be a given, to AB, well, I know I have a 90-degree angle right there, which also means that that has to be 90 degrees. They are a linear pair. So I can clearly state that APC is congruent to angle BPC. And I'm willing to take, I mean, you could write that they're both right angles, but why don't we just write, definition of perpendicular doesn't sound quite right. Transitive property with perpendicular, but let's just write both 90 degrees. This one isn't going to show up a lot until 7.5, and then what we're actually going to do is state that they are right angles, and that's going to help us use our hypotenuse leg. You have no idea what I'm talking about, but you will later. 10. We've already used 10 quite a bit. I like to call it the dove property because while all postulates should be obvious, this one always seems particularly obvious. If we share a side, we know that side needs to be congruent to itself. So if I have a situation like this, well, what I know is if I'm really trying to prove these triangles congruent, this upper triangle that I just highlighted in yellow and the pink triangle below share a side. Notice how that changed colors to orange. That's a big old hint that we have SG on the upper triangle is congruent to SG on the lower triangle because it's the same thing. And you could write reflexive property of equality, but if you write reflexive, I am perfectly happy. Dog gives you half credit. Now we have mostly seen this so far, we have only seen this so far